So next, we consider three-connected graph. So as we see, the motivation for studying connected graph was that any graph is disjoint union of connected graph. So that was very simple to understand. So we have just disjoint union. Here you have graph, and then between them there is nothing. And studying for two connected graph was we have this block cut point graph. So last time I said block graph as you have A and then B, you have blocks, and then cut vertex, and then this bipartite graph is tree. So I told you the name was the block graph, but it's actually block cut point graph is the proper name of this bipartite graph, which is forest. And yeah, this gives a motivation for studying two connected graphs. And two connected graphs are essentially, all obtained by year decomposition. So unfortunately, if we go higher connectivity, we don't have this kind of structure. You could consider, maximal three connected graph, but the structure you get is much more complicated than this kind of simple structure. And also, year decomposition was, relatively easier to understand, but for the three connected graph, if you consider, the things that we will learn are, more complicated and it's less intuitive. However, it could still show that this vertex tree split. So we learned about this vertex tree split before. Using this vertex tree split, we could, generate all possible three connected graphs. And for, in order to discuss this in more convenient way, we want to first define the following operation, which is the inverse operation of the vertex K-split. So what is the vertex K-split? So you have a vertex, then you split it into two adjacent vertices. So that was what vertex K-split is. In some way, you tear the vertex into two vertex. And this, you have one vertex and then you tear it into this edge. And we want to define the inverse operation. We want to merge these two vertices into one, or more of contracting this to one. So given on H, E, then a graph G, we define the contraction, and we write G slash E. This is the graph obtained from C by replacing the endpoints of E with so this operation, single vertex. Whose neighbors are their neighbors in G of side effect E. So you have X, Y, A, B, C, D, E, F. If you contract it, you have one vertex, A, B, C, D, E, F. And all of the, if a vertex is adjacent to at least one of them, then that is adjacent to this new vertex. And we say that this G contraction E is obtained from G by contracting this G. And we say a K contractible H is an H. First, contraction leaves a K connected. Again, the graphs are the model, mathematical model that we use to encode the essential information about some given problem. And there are many problems that we consider. And in some context, when we are more keen on how the edge changes, we might want to actually define this contraction so that in a slightly different way, that by specifying not just neighbors, but we replace it to a new vertex, which is incident with all the previous edges. In that case, a multi-edge might arise. So in many contexts, this is more actually natural definition for the contraction. But in our course, we keep with this definition so that we already get simple graph. So the multi-edge cannot arise. And with this definition, we can prove the following lemma, called the contraction lemma, proved by Hutt in 1961. He proved that every three connected graph other than K4 has three contractible edges. Then what's the, before proving that, what's the consequence of this lemma? So this said that every three connected graph other than K4 has three contractible edges. So if you have a three connected graph, and there is an edge, and once you contract it, and this is still three connected, and you keep do that, and by this lemma, anything other than K4 has three contractible edges. So this will, and every time the number of vertices decrease, so this will end at some point. You can do it at most n time, and then you can only end with the K4, right? And what's the inverse operation of this? Inverse operation is vertex K split. So to be more, precise, vertex 3 split. So that means whatever three connected graph you start with, this can be obtained from K4 by sequence of vertex 3 split. So this that our graph is three connected if and only if it can be obtained from K4 by a sequence of vertex 3 split. So this theorem is easy consequence of this lemma. And this gives us what we want. This gives us the operation, preserve city connectedness. And then, starting from K4, you apply this operation repeatedly, then you can obtain any city connectedness. This provides us the understanding on city connectedness. And let's prove the theorem, the lemma. So let's see the city connected graph. Sorry, that was anyway, yeah. Maybe I should top my phone. So, and it has, let's say it has at least 5 vertices. So, if G has those 3 contractible edges, then what do we know? Then, no matter what edge you take, G contracting E has a separating set of size 2. And how does it look like? So you have a graph, and then let's say you contract X and Y. Then you have new vertex you obtain here. Let's write X, it is X star Y. And there you have a separating set of size 2. If this separating set is here, that doesn't contain this X star Y, and X star Y is somewhere here, and these are disconnected. And in the original graph, if you go back to the original graph G, you have X, Y, and the same 2 sets, so that this set of size 2 is again a separating set in your original graph, which is contradiction because G is a 3 connected graph. So that means this separating set must contain this X star Y inside of here, which they consist of the vertex obtained by contracting E and some other vertex C. So you have C and then X star Y. So let this E be X, Y, and this is the picture. Then what? Among all the edges in G, we choose an adjacent pair X, Y, and say their companion G. Let's write G as G sub X, Y, which is G. Meaning that this picture, together with this X star Y and then G, they form a separating set of size 2. And we choose that how so that the resulting disconnected graph G minus X, Y, G. So this disconnect the graph G contraction E means that in G you have X, Y, G, and then this also disconnect the graph. This has a component H with largest possible order, meaning that for each choice of x, y, you find this companion G and then delete it, then you get this component. You choose the biggest component, and you do this for all edges. And for each x, you have a specific size of H. And out of all choices, you choose the x, y, so that this is the biggest. And let's say the other one is H prime. So let H prime be another component. There could be a third one, but let's say it is another component. So it's graph G minus X, Y, G. Then what do we know? This X, Y, G is a minimal separating set because G is 3 connected. What do we know? That means each element in X, Y, G has a neighbor in both H and H prime. Because if that's a neighbor, but it doesn't have a neighbor to H, then we could just delete X and Y, and then this only separates H from the other. By the same logic, if only this two has a neighbor in H prime and X doesn't, and just deleting this two already separate H prime from the other part. Then let's say you have a neighbor of G in H EU, but U, the A neighbor of G in H prime. Then what? This GU is an H. That means there exists a P, which is G sub GU, meaning that it's companion of this H GU, such that GUV is a separating set. So you have X, Y, G, U, it's a H prime, H, and H is as large as possible. This is the picture. And where is B? So this together with B forms a forms a separating set. And let's see this graph. H together with X and Y. So if let's say the subgraph of G induced by the vertices in H together with X, Y is connected. Of course, this H is a component, so it is connected. And then we add two vertices which have neighbor in H, so this is connected. Moreover, we don't know where this B is. If B might be in here or might not, even if it's there, if we delete this vertex P from this graph, let's say if it's here. If not, we don't have to delete anything. We know that this does not disconnect. let's give name to this graph, say G prime. This does not disconnect G prime. Why? If it disconnects G prime, then what happens? B, this is how G prime looks like. And where is X and Y? If X is here and if Y is here, then B does not disconnect, right? So at least one part, no X and Y here. For all we know, B could be one of X and Y. We don't care. So we for sure that there are only one part with the X and Y, maybe X or Y here. But here there are no X, Y. Then what happens? The outside part, this does not send any, this sends edges, this might send edges to here because this is sending edges to X and Y. But there are no such edges here because there are no such edges from here to here. This is a concept. So there are no edges from here to here. Only G should have edges. That means these two vertices, this connects this, let's say this is H1, H2 from other. So this is a contradiction because the original graph is 3 connected. There are no separating set of type 2. So we know that the deleting B does not disconnect this graph G prime by as otherwise CV is a separating set of G as we described here. Hence, what we know is G prime minus B. So this does not separate into two. This lies in a component of G minus C U B. But how many vertices does it have? G prime has a number of vertices in each, plus you add 2. And then possibly, I mean, if G lies there, then we subtract 1, otherwise not. So at least it's many vertices. Which is more than the number of vertices in H. But what was the definition of H? H was the one that we choose XY so that once we delete these 3 vertices, this is the largest possible component. But here, now we found this G, U, B, so another edge whose deletion of this corresponding vertex code of type 3 leaves the component X minus B, which is bigger than H. This contradicts the choice of X, Y, G. This is contradiction as G contains 3 constructoblets. And this proves what we want. So again, this had consequences that no matter what K-connected graph you have, you start from K4 and you do the vertex K split to reach there. And then while you're doing that, 3 connectedness is preserved. So you can reach there. One might ask that what if we consider 4 connected, 5 connected, 6 connected? can we do the similar thing? Can you always use vertex 4 split, vertex 5 split to obtain what you want? And that's actually not true. For K at least 4, there are infinitely many graphs, which is like a K connected graph that contains no K contractible edges. So for higher connectivity, I mean, this idea of finding some operation which preserves the connectedness while it creates all possible K connected graphs. So that works for 2 connected graphs and 3 connected graphs. However, for higher connectivity, such a plan would not work. So instead, for this higher connected graph, we want to focus on studying its property. Instead of trying to completely understanding its structure, we want to rather focus on its property regarding connection. The connectivity, the connectedness was, first considered for finding a path between those two, so that the connection was the original motivation of considering this connectivity. And now we generalize this part of connectiveness into connectivity. 2 connected, 3 connected, so those are all about connectivity. So in the next video, we will study about the connection property that's guaranteed by connectivity. So when some graph is, say, 10 connected, how strong connection, how robust connection can we guarantee between certain vertices? So we will talk about that in the next video.